Well, we talked about lines last couple of days. In fact, we've talked about lines a lot since grade 9. That's a big part of everything that we've kind of done is just talking about lines, equations of lines, all that good stuff. And, over the last couple of days, we saw some different notation that we can use to talk about lines. And again, it all comes down to the properties of those lines, right? Like that's what questions always boil down to. So as an example, we've got equation of a line here. Okay, we've talked about that. That's a scalar, the general scalar form of the equation of a line. And it all comes down to, as I said, properties of the line. So in this case, very nicely, we can get the normal. We've talked about that's actually very useful. And from the normal, we can get a direction vector. And, all the different things that we've talked about in terms of vectors come into play here. So, we want to think about things like the dot product of the normal or of a normal vector and a direction vector is going to be 0. And that's just one of the sort of properties or one of the things that we can think about in terms of lines. And there's all kinds of other ones as well, right? And so when we start to think about a line, we want to think about all of those things that are properties of the line or that might come up in the different kinds of questions that were asked. Okay, and as usual, visualizing this stuff is really good. So I've got a line, okay, and it's going off in both directions forever. And it has a normal. It has a direction vector. And not a unique one. We could have, a variety of direction vectors if we wanted to that were all scalar multiples of each other. We might call this the line L, and direction vector, normal, and all kinds of things like that. And again, keeping in mind that direction vector doesn't have to be in line with the line, right? Vectors don't exist in a particular position, so that's really important to always remind ourselves of that. That a vector will be parallel to a line, but it doesn't have to necessarily be in the same place as a line. In fact, vectors are not in particular positions. Okay, so that's everything that we've kind of talked about with lines. Talked about all the different kinds of equations. We're not going to go over all of that right now, but all the different forms of equations of lines. And we have talked about lines, as I said, from grade 9 in 2-space for years. We've also talked about them briefly in 3-space. And the different forms of equations that they can have and the different properties that they can have, and questions involving lines like, is a point on the line, that kind of thing. Are two lines parallel, perpendicular, neither, all those kinds of things, right? So today we are extending this idea of equations of things or things that exist in space. We are extending this to planes. And that's what today and the next few days are all about, is planes. So in 2-space, lines are really where it's at, or curves. But once we go into 3-space, we also have other things that we can talk about. And I think we mentioned this, that ax plus by plus c equals 0 is the scalar equation of a line in 2 space, and there is no scalar equation of a line in 3 space. Okay, so that's important. Knowing what can and cannot be represented with the different forms is very important. And it turns out that we sort of can connect the fact that there is no scalar equation of a line in 3 space because the scalar equation is a plane. It's not a line in 3 space. That scalar equation is a plane. So ax plus by plus cz plus d equals 0 is the scalar equation of a plane. And what's really nice is this scales up from 2 space to 3 space really naturally, in that the normal of this plane is a, b, c. Okay, and again, there is no scalar equation of a line in 3 space. Okay, and we're going to talk about properties of planes and all the different kinds of things we've explored with lines. We're going to do a lot of the same stuff with planes. And we're going to talk about different forms of the equation. The same way we have different forms of equations of lines, we're going to do the same thing with planes. But before we get to any of that, what is a plane? Right? Like, a big part of this is visual. So what is a plane? Well, we're going to look at this in a couple of different ways. And here is one. So this is 3 space. And we have talked about this, and we've seen vectors in 3 space. So we have the x-axis, the y-axis, and now a z-axis as well. Okay, so we're going in 3 directions, 3 dimensions. And what is a plane? Well, that's a plane. So in 2 space, the entire grid is the plane. We are graphing on that 2-dimensional plane. But once we get into 3 space, we can have multiple planes. So infinite planes, just like we can have infinite lines that have different slopes at different angles. The same is true of planes in 3 space, and we can see this one, and we could imagine other planes in this space that could interact with this plane, or just look different from it, whatever, right? So that's what a plane is. A plane is like a flat sheet of paper that exists in space. And an even more interesting way of looking at it is
so we're going to use this app Geogebra, which I've talked about a lot and used on the computer, but apparently there is an app for phones. I think it's available for iPhones, and it's definitely available for Android phones, that allows you to graph all kinds of things in 3D. For us, we're going to do lines and planes. And we've looked at that a little bit already, but it has this on the phone. It has this really cool AR mode, so augmented reality. So let's watch. The first thing that I'm going to do is move the phone around, and notice how it's detecting the surface of this table, and when I touch the screen, it will put whatever I have graphed, which right now is nothing, so it's just axes, but it's put them on the table. So just that is pretty cool. Amazing how it tracks. And I can walk around. In fact, I can walk around the room, back up, and it knows where that grid is supposed to be. Okay, so we're going to use this to visualize a plane. So what is a plane? And if I turn this on, there we go, we have a plane. And as I said, everything we've done has been in 2 dimensions. And so we only had one plane. But now that we have 3 dimensions, we can talk about a plane existing in this space. It's like a piece of paper that I just hold out in space. Okay? And it has an equation. And I can tilt it if I change any of these coefficients, but let's say I change the coefficient of the z. Notice how it tilts it down. Okay. I'm going to put it back because I don't like that. Okay. And I've got this set up so that I can drag the constant, and I'm kind of just, it's almost like just changing the y-intercept of a line into space. I'm just kind of dragging it up and down. So this is what we're going to talk about. We're going to talk about equations of planes, and you can see that this one is just x plus y plus z equals a. So if a is 0, that's what we started with, but I can change it, and it just kind of moves the plane around in space. So I'm going to put it back, and there we go. And like lines, what we're going to explore is the properties of planes. With lines, we talk about their slope. Planes are going to have something similar to slope, but we don't call it slope. But we're also going to look at things like points and whether or not they are in the plane, just like if a point is on a line. So let's see if I can do this. This point right here, whoops, is in the plane, isn't it? I mean, look at that. And that point, which I believe is point A, -1, -2, 1, will satisfy the equation. Right? X plus y plus z equals 0. Now this point down here is not in the plane. And I can see that it's just out in space. And that point is -1, -2, 3. Okay, and that is the kind of thing that we're going to talk about. But visualizing this stuff is going to be so important. And using an app like this is really, really powerful. To think about the interactions. In the first half of this course, we're getting used to the notation, and we're just thinking about these kinds of things. Is a point in a plane? What's the equation of a plane? The different forms of the equation of a plane. But in the second half, again, we're going to start to do some other things that involve the interactions of lines and planes, and the visualization is going to be really, really important. If I change this, in fact, well, let's just make it 5. Oh, that was the wrong one, but notice now it's not in the plane. So that one up there, I moved, no longer in the plane. Okay, so you can use this app on your computer and just spin it around on your screen, but if you can get it on your phone and do this augmented reality version, it's pretty amazing.
Okay, so that's pretty cool. And, visualizing all this stuff is going to be so crucial. In the second half of this unit, we are going to do a lot of work with all kinds of different things in three space interacting with each other. And, the visual aspect of it is going to be paramount. Like it's so important. So keep this in mind. We're going to get into the algebra of all of this, as always, but we really do need to bring it back to the visual and think about what this actually means, what it looks like. It's going to help us solve problems. It's going to help us decide what to do in all the different kinds of questions that we're asked to do, right? So keep that in mind. Okay. But another thing that we can do is we can draw these. So that was all a very good representation of planes, of three-dimensional planes, like planes that exist in three space, but representing them with technology is fantastic. But what if we can't do that, or we want to try to represent them in two space? So this is how we can do it. There's a plane. The normal of the plane is at a right angle, okay? It's orthogonal, or it's perpendicular to every direction vector that is parallel to the plane. So this is a bit tricky, but direction vectors don't necessarily lie in the plane because vectors don't exist in a particular position. But we can think of them as in the plane, but they're not. They're parallel to the plane, okay? But if we sort of align them with the plane, then it's kind of like they're within the plane. And the normal is going to be perpendicular to all of those vectors, right? So that's really important. And it turns out that the normal of a plane tells us more about the plane than anything else. It's actually the most important algebraic property that we can have about the plane, because you can have an infinite number of direction vectors. Take a look. I can have vectors going this way and this way and this way, all over the place, right? Every which way, and they are parallel to the plane because it's not a line, it's a plane. But there's only one normal, or scalar multiples of that normal. There's only one normal of the plane. So that ends up telling us a lot more about the plane. Something else is we often denote planes with pi. So plane 1, plane 2, pi 1, pi 2. Okay. We can have points in the plane, points outside the plane. All of the same things that are true of lines, points on the line, points not on the line, are going to be true of planes. And this is the kind of thing that we want to start thinking about, is these properties of planes. And we're going to start to do the algebra involved with determining these properties, and determining things like, is the point in the plane, that sort of thing. Okay. Before we get into those specifics, some definitional stuff. A plane is a surface such that any straight line connecting 2 points in the plane lies entirely in that surface. So an example of a plane is very similar to the one that we just saw. And if I have two points and I connect them with a line, that line lies entirely in that surface. What would this look like if it were not a plane? Well, something like this. Okay, so I have something that could be thought of as like a piece of paper that's been bent and folded in space, okay? And I've got 2 points, whoops. And the line that connects them is not within that surface. It leaves the surface, and so that would not qualify as a plane. This definition is not something that's going to be important for us. We're not going to look at the difference between something that's a plane and not technically a plane, like a curved surface. That's not what we're worried about. But be aware that this is a definition that, you know, same thing as the difference between a straight line and a curve. You know, we could explore that same idea of a plane by the strict definition versus a curved surface. And that is again another element or extension of mathematics that if you continue to explore this, you would look at the properties of those other curved surfaces. But we're going to look at planes. So that's what we're worried about. One thing that will be important to uniquely define a plane. Now, there are more than just the ways we're going to explore, but this again is going to be a really useful way of thinking about this, because if you have to come up with the equation of a plane, then you are going to look at, you're going to look for sort of one of the couple of criteria that we're going to talk about, right? So to define a plane, we need either 3 points in the plane. These points cannot be collinear. What does that mean? Well, they can't be in a line with each other, right? Because if we have 3 points in a line with each other, that's not really different from having 2 points. So we could imagine these 3 points as making a type of triangle in space. Okay, another way that we often say this, and this is a term that we need to know in this course because it's something that we're going to use, is we call this linearly independent. Okay, so that's a term that we need to know. Another way that we can define a plane is 1 point that's in the plane, and 2 vectors that are parallel to the plane and not collinear to each other. Because again, if I have 2 vectors that are collinear to each other, then they don't really give me new information. Now, as I said, there are other ways that you could define a plane. You could define planes with lines. Lines are not the same as vectors. Okay, so 2 vectors and a point, 2 linearly independent vectors and a point will define a plane. But as well, lines, 2 lines that are not collinear or not coincident will define a plane. 3 points define a plane. There are other ways, but these are the 2 main ways that we're going to look at that will define a plane. Okay, so when you are asked to determine the equation of a plane, you're basically going to look at, generally speaking, one of these 2 ways. There may be some other instances where we push you a little bit to think, and you may have to sort of visualize or think a little bit beyond the properties of these 2 specific definitions, but these are the 2 that we're going to start with and we're going to focus on for the next little bit. Okay, and it's just like coming up with the equation of a line. A line is defined by the slope and a point kind of thing. This is the same idea. Okay. And now what we're going to do for the next several days is just do some work with the algebra involved in working with planes, getting used to the different ways that we can express their equations, and determining properties of them, or just doing things like is a point in the plane, all that kind of stuff. Again, just to get used to the notation and get us visualizing these things and thinking about it, right? So keep in mind as we work through this over the next few days, that's what this is all about, is just getting used to the idea of planes. Okay, so first question, here you go. Given the scalar equation of the plane, x plus 3y minus 2z, okay? And this is, again, something that we want to get used to is like, how do I know that this is a plane and not a line, right? So when I see this scalar equation, x plus 3y minus 2z minus 10 equals 0, that's a scalar equation. How do I know it's a plane? Well, the fact that it has a z means it's in 3 space, and there is no scalar equation of a line in 3 space, so this has to be a plane, right? And that's one of the things that we just need to know and need to get used to, and all the stuff that we're going to do is going to help us remember those kinds of little details. Okay, so this is definitely a plane. Determine if the points A and B are in the plane. How are we going to do this? We're just going to do a left side, right side check. The X, Y, and Z coordinates will have to balance the equation. Okay, so for A, we've got the left side, which is equal to x plus 3y minus 2z minus 10, and the right side is 0. And so that's 1 plus 3 times 3 minus 2 times 0 minus 10, which is 1 plus 9 plus 0, or minus 0, minus 10, which is 0. Therefore, A is in the plane. What about B? So we've got 2 plus 3 times negative 3 minus 2 times 4 minus 10. Right side is 0. Whoops, not equal to the right side. This one was equal to the right side. Therefore, B is not in the plane. Okay. Vector equation of a plane. Well, we talked about how 3 points are required to define a plane, or 1 point and 2 non-collinear direction vectors. So that means the vector equation of a plane is going to be in 3 space, and it requires that point and 2 parameters, direction vector 1, so s times direction vector 1, and t times direction vector 2. I need 2 direction vectors. That's what we talked about that is required to define a plane. So my point could be x naught, y naught, z naught, plus some parameter s times my first direction vector. And then my other parameter t times my other, direction vector. Okay. So this is where P is a position vector. That goes to a point in the plane. And D1 and D2 are direction vectors, or vectors parallel to the plane and not each other, as I said before. if we have two vectors that are parallel to each other, they don't give us new information. So they have to go, point in different directions, and that will give us new information. Okay, and I don't know if this seems simple or straightforward, but it's really, really important that you think about the relationship between the direction vectors that are parallel to the plane and how they can point in all kinds of different directions and how they can help define the plane and a point in the plane, and how all these things are related, like, is really, really important. Okay. All right, let's do some more questions. Find the vector and parametric equations for each plane. So this one is giving us two direction vectors, vector A and vector B, and a point in the plane. And the point in the plane will give us a direction vector. That means I can define the plane and its vector form of the equation of the plane as the position vector, okay, which is the vector to that point, right? And the two linearly independent direction vectors. And then what about the parametric equation? Well, as you would probably imagine, it's the sort of same idea as with lines. We just separate the x component, y component, and z component separately, right? So it's x equals 0 plus 5s, so 5s and minus 2t, right? But the 0, so that part's gone. So 5s minus 2t. Y equals 1 minus 3s plus 5t. And z is 5 plus 0s, so I'm just going to leave that out, plus 7t. Obviously, we want to streamline this, and if we have zeros, we want to leave them out, but don't be confused by the fact that there's some constants and variables missing. It's because of the zeros that are in the vector form of the equation. Okay, and again, understanding the vector form and the parametric form and being able to go back and forth between the different ones and get direction vectors out of them and get points out of them, and all that stuff is, all things that we're going to have to know how to do. So we want to get used to the different forms of equations of planes, just like we did with lines. Again, find a vector and parametric equations for the plane that contains this point is parallel to, well, what is this? How do we recognize what that is? It's a line. Why? Because it only has one direction vector. Okay? So planes have to have two direction vectors. So when I look at the equation of a plane, it's got two. But if I see something, but the fact that it has x, y, z just means we're in three space. Okay? So when I see x, y, z, and then I look at the rest of the equation, it only has one direction vector. That means it is a line. And again, it's something that we have to pick up on and understand, quickly and easily, kind of thing. That is a line. That's also a line. So I've got two lines. It contains a point and it's parallel to these two lines. What does it mean, parallel to these two lines? Well, it means that those direction vectors of those lines are parallel. So I can use these direction vectors as the vectors to define my line. So I'm going to use the position vector of the point that I was given that's in the plane. And I'm going to use my two direction vectors and then just write the equation. And when we're using parameters, I've said this before, we have to use different parameters. You noticed up here that there's an S and a T, okay? And that S and that T is not necessarily the same as the S and the T in what I'm using, but generally speaking, when we're doing equations of planes, we use S and T, and you can't use T and T. They have to be different parameters, okay? That's really important. -1, 5, 4. But they do not in any way have anything to do with the parameters that were from those lines, okay? We're just reusing the same variable, kind of like y equals mx plus b. M is always a slope, even in different lines, okay? And then in parametric form, we've got x equals 4 minus s plus 9t, y equals 0, okay? So 5s minus 2t, and z equals -6 plus 4s minus 3t. There's parametric form. All right, let's keep going. Something else very different. Find the, what are we supposed to do? Find the equation of a plane that has these three intercepts. How are we going to do that? Well, basically what this is doing is giving us 3 points, right? It's giving us the three intercepts, but that's 3 points. And so let's just visualize this. Oops. So there's Z, X, and Y. And the X-intercept is 2. The Y-intercept is 3. The Z-intercept is 4. And so that defines the plane, right? And now I've just drawn a triangle, but you can imagine this plane extending out and sort of being parallel to that triangle, right? But I'm going to leave it as the triangle like that. We need to know the coordinates of these points. So this one I'm going to call R, and it is 0, 0, 4. I'm going to call this one P, and it's 2, 0, 0. And I'll call this one Q, 0, 3, 0. So this is, I think, fairly straightforward, but again, a little bit different from working in 2-space, getting used to the idea of having 3 coordinates and thinking about intercepts in on 3 axes, that kind of thing. So it's worth sort of spending some time and thinking about it and making sure you understand this. Okay, how do we come up with the equation of a plane? Well, we need 3 points. We have that. But the actual vector equation of a plane requires a position vector to a point in the plane. So we can pick any point we want. And then 2 direction vectors, right? So let's say I'm going to pick, and again, when you're presented with a question like this, it's going to be something that you know how to do. You're going to have the skills to be able to do this, but you might not know what to do. You might not recognize, hey, I have to do these 3 steps to actually answer this question. So coming up with the equation of a plane, I need 2 direction vectors, and I need a point in the plane. I'm turning the point into a position vector, so I'm just going to pick one of these 3 points. So I'm going to pick the x-intercept. And then how do I come up with 2 direction vectors? Well, how about vectors between the 2 points? So PR, how do we find the vector between 2 points? Subtract backwards. And we've said this over and over again now. This is a really important skill. You got to know how to do this. So it's R minus P, right? So 0 minus 2 is -2. 0 minus 0, 4 minus 0. And second direction vector, how about PQ? So again, negative 2, 3, 0. Therefore, my equation becomes choose my parameters, and there we have it. And you probably are really starting to see how, there's no one single answer for this. So on a quiz or a test, or if you're doing questions from a textbook or whatever, and you look at the answers in the back, your answer may not match because I could have chosen any point to create that position vector. I could have chosen any 2 points to make the direction vectors, and I could have pretty easily could have a large variety of equations that look a little bit different, but they're all this equation of the same plane. Okay, so keep that in mind. And then turning this, hopefully this is getting to be old hat already, but turning this into a parametric equation. Got lots of zeros here, so that's just y equals 3t. And z equals 4s. All right, find the scalar equation of the plane in part C. This is different. How do I do this? Well, how do we do like a scalar equation? Ax plus by plus cz plus d equals 0, where the normal vector is a, b, c. So, as I've said, this is a big deal. This is important. What is true of a normal vector? It is perpendicular to the plane. So if I have 2 direction vectors, there's only one vector, scalar multiple of it, but one vector that is perpendicular to both those vectors. And if you remember from Unit 7, that comes from the cross product. When you take the cross product of 2 vectors, you get a vector that is perpendicular to both. And that vector is unique, or that family of vectors that are scalar multiples is unique, right? There's not multiples of those. So in order to find the normal of a plane, I can do the cross product of the 2 direction vectors that I know because I've already written out the vector form of the equation of the plane. And that will give me the normal, and that's going to be a really good start. So we're going to start with that. So start by finding the normal vector. Okay? And I can say some constant times the normal vector is going to be the cross product of the 2 direction vectors that I have. Okay, and doing the cross product of these 2 vectors, I've got 0, 4, negative 2, 0, and 3, 0, negative 2, 3. And if we're not fresh on how to do the cross product and dot product and all that stuff, we got to get there because this is something that we're going to do a lot of, right? Cross product is going to be a big deal, so we got to make sure we've got that. So this is going to be negative 12, negative 8, negative 6, okay? Just doing the calculations required. And the reason why I call that Kn is because I might be able to simplify this, and that's just going to make my life easy. So I'm going to divide it by negative 2, it looks like, and that's going to give me 6, 4, and 3. And isn't that a little bit of a nicer normal to work with than the original one that I got from the cross product? Okay. All right, so that gives us the normal. is not the equation, but it will give us this 6x plus 4y plus 3z plus d equals 0. So all we're missing is the d. And to find that, this is something we've done all the way back to grade 9, is we can sub in a point. So the nice thing about this is I have 3 points and they are intercepts, and intercepts have zeros, so that makes my life easy. So I'm going to sub that in. So I've got 6 times 2 plus 4 times 0 plus 3 times 0 plus d equals 0, which means looks like d is negative 12. And so the scalar equation, is 6x plus 4y plus 3z minus 12 equals 0. And sometimes you see that with d on the other side, so equal to 12, but we're going to leave it that way, equal to 0 for now, okay? Finding the scalar equation of a plane is something we're going to do a lot of, so you really want to make sure you've got that, you understand that, why we did the cross product and how we came up with the normal, and the normal to a plane being an important part of it, coming from the scalar equation, but also using it to develop the scalar equation. Like, this is a big thing. Okay, this is something that we're going to do a lot of. So get used to that and keep that in mind. That's something that you really want to be comfortable with. Okay. All right. So find the scalar equation of the plane. I think we've got that. So example 3, find the intercepts for x, y, z. Okay. How are we going to do this? It's interesting. Back in grade 9, we did y equals mx plus b and standard form. And we get to calculus and we look at vector form and parametric form. And I talked a lot about how important parametric form is. Like, it's a big deal, right? Parametric equations are a big part of the next sort of stage of mathematics. That being said, it turns out that when we're working with planes, the scalar form is actually really useful. So often the scalar form is the one that we want to have in order to do the different things that we're asked to do. So when you are asked a question like this on a quiz or a test, you have to know that what we need to do is turn this into scalar form. Okay. And when we have it in scalar form, then we're going to be able to come up with the intercepts. So I'm going to make a note of that. Convert to scalar. And so how do we do that? Well, we need to come up with the normal. So again, I've got -3, 5, 2, -3, and 0, 6, 4, 0. And that looks like -18 minus 0. And that looks like 20 minus 12. So again, I'm doing this, that. So -3 times 6 minus 0 times 5. Then 5 times 4 minus 6 times 2. Then 2 times 0 minus 4 times -3. So that looks like positive 12. And again, if I can simplify this, it might just make my life easy, which in this case I can. I'm going to divide again by -2. There is definitely no rule that the x coordinate has to be positive, but you'll probably notice that people often do that. Okay, so there's my D. And what point am I going to use? Well, there's a position vector to a point in the plane. So I'm going to use that. Whoops. 1, 2, 3. So this is going to give me a d value of 17, I believe, and therefore the scalar equation is 9x minus 4y minus 6z plus 17 equals 0. All of that was so I could come up with the intercepts, and the x-intercept will occur when the y and z coordinates are 0. So if I put 0 in for y and z, okay, I end up with, I'm going to show this for the first step, but generally you probably wouldn't. Let me do this. So x-intercept, set y and z equal to 0. So I've got 9x minus 4 times 0 minus 6 times 0 plus 17 equals 0. So move the 17 over and divide by 9, and my x-intercept is negative 17 over 9. See how that works? So the 17 moved over, and I just divided by sort of the coefficient of the x term. And so similarly, the y-intercept will be, looks like positive 17 over 6. Nope, sorry, not 6, 4. The z-intercept is 17 over 6. Okay, there's my 3 intercepts. Finally, I hope that was okay. The big takeaway from that, yes, the idea of subbing zeros in, but the bigger idea was, hey, this question was actually asking me to rewrite this in scalar form. Okay, and you're going to notice that's a common theme. That's something that we're going to do often. Scalar form of a plane is really useful. Determine if the point is in the plane. Well, how are we going to do this? Hey, scalar form. Same thing. We have to convert this to scalar form. Then we can do a left side, right side check. Could you do it in vector form? It's possible, but you would have to sort of by inspection figure out what parameters of S and T would sort of make this work. And that could be really difficult. So honestly, the easiest way is to convert it to scalar. So again, we're going to do the cross product. And you've probably noticed we are often going to add that constant in because we like to simplify it if possible, but we're going to see different instances of where simplifying it is going to work, and sometimes it's not, right? It's not going to add a lot of value. But anyway, so let's see, 1, 4, 0, 1, 5, 6, negative 1, 5. So just writing that out to do the cross product. Okay, so 6 minus 20, that's going to give us negative 14. I've got negative 4 minus 0, so negative 4. And that looks like 0 minus negative 1, so that's 1. And here's a great example of, I can't do much to this, but 1 negative is probably better than 2 negatives, so why not switch it to that? If you didn't do this, not going to be the end of the world. There's no rule about what normally you have to come up with. We generally would have it simplified. So I wouldn't use 28, 8, and negative 2, but there's no rule that it has to be fully simplified or it has to have negatives in certain places or anything like that. So 14x plus 4y minus 1z minus z plus d is 0, and again, picking a point. And determine if the point is in the plane. So that position vector goes to a point in the plane. So I know I can use that point to come up with the equation of this plane. So plus 3 minus negative 3. And that's going to give us a d value, I believe, of negative 51. So my equation is going to be 14x plus 4y minus z minus 51 equals 0. All of that was just to figure out if this point, so now I'm doing a check, 4, -1, 1, left side is 14 times 4 plus 4 times -1 minus 1 minus 51. And that looks like 0. And the right side was obviously 0, left side equals right side. Therefore, the point P is in the plane. And again, this is something we talked about, sort of for this whole unit, is when you get a question like this where it says determine if the point is in the plane, and it gives you the plane in a vector form, or maybe it gives it to you in parametric form or something like that. It's not explicitly saying convert this to scalar form and then do this, but you have to know that that's what you're going to do. So a question like this on a quiz or a test, part of that is testing that you know to convert it to scalar form and that you know how to convert it to scalar form, right? So that's a big part of the first half of this unit, is all these different little questions that just ask you to check things about points, or as I said, rewrite equations into different forms, or come up with properties like normals or direction vectors, or all those different kinds of things. These are like there's underlying questions often involved in all of these, like converting it to scalar form or whatever it happens to be, right? So keep that in mind, that that is really part of this. And it's in a way by design that the questions are not going to tell you what to do. They're not going to say convert it to scalar form and then do this. They're just going to say determine if the point is in the plane, and you have to know that that involves scalar form, okay? Worksheet is only part of it today, and I believe some of it will be assigned in the future, or if you want more practice, there's nothing wrong with the rest of the worksheet, okay? Good luck. Keep in mind that idea of planes just in general, visualizing, let's see here it is, visualizing what a plane is and how you can have points in the plane and direction vectors parallel to the plane. This is something that's going to be this visualization is going to be a big, important part, I think, of being successful and really understanding it and being able to problem solve and decide what to do in all these different situations. Okay, so keep that in mind. If you have to, start graphing it with technology, or even just play with pencils and paper in space. I often, when I'm thinking about planes, I'll hold up a piece of paper to represent a plane, right? So it's something else that you can do.